Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hey there, Chapter 4.6, Historical and Exponential Depreciation. So the objectives of this lesson are to write, interpret, and graph an exponential depreciation equation. Manipulate the exponential depreciation equation in order to determine time, original price, and depreciated value. All right, so there's a bunch of vocab here. Let's start with dollar value. Dollar value just simply means the value of money that something is worth, depreciates or appreciates. Historical data, the prices from the past that a car was worth. Historical depreciation is the devaluation of a car using historical data. Exponential decay, rather than the value decreasing by the same dollar amount each year, which is linear, it decreases by the same percentage each year. Exponential decay. Exponential depreciation is the model of exponential decay in the context of auto devaluation. And exponential regression is the process of arriving at an equation for the exponential curve that best fits the set of data. We'll use a TI calculator for that, or possibly Desmos, we'll see. Geometric sequence is a sequence in which each term is found by multiplying the preceding term by the same value. And the geometric progression, a type of sequence where each succeeding term is produced by multiplying each preceding term by a fixed number. And that fixed number is called the common ratio. It's the amount between each number in a geometric sequence. Okay, example 1 says to determine an exponential depreciation equation. Okay, so we need to determine an equation. So let me get my highlighter here. Determine an exponential depreciation equation that models the data in the table from the previous page. Well, this came from the previous page. So what we're going to do is we're going to get our calculator out. And to do an exponential depreciation or any regression equation, we first of all have to enter this data. And there are 10 pieces of data here. So age is going to be our X and value is going to be our Y. So we go to Stat, Edit, and I'm just going to go up and clear this, arrow up to L1 and hit clear and come back down. So age is going to be our L1. So I'm just going to simply type in 1 through 10 here. So 1, enter, and so on. Okay, so I'm up to 10 and then I arrow to the right, and to go with 1, I have 24,230. And I'm just entering these as we go. 22,355. Okay, I'm just going to continue entering these. 20645. Hello. 20645. Enter. 18070, 16265, 15245, 14075, 13100, 12325, and 11525. And they match. Okay, so always check, make sure your X's and Y's have the same value, or you're going to get an error mismatch. So we want an exponential depreciation equation. So we're going to do an exponential regression. So now that I've got the data entered, now I'm going to go to the home screen. I'm going to press Stat, Calculate, and I'm going to arrow down until I find X regression, which is 0, and hit Enter. L1 is X, L2 is Y. Frequency, store, and calculate is all just left alone. And there is my equation. So I'm going to write that down. Okay, so my equation is going to be Y equals and A is 25,921. And I'm going to go out a couple decimal places. I'll just go to 2.87 times B to the X. So B is 0.91896 to the power of X. So there's the equation. Determine the exponential depreciation equation that models the data. So there it is. And if I rounded, then it would have been 0.0 or 0.92. Okay, I could have rounded this to 92 to the power of X. All right. So then it says, how might it better fit a better fitting exponential depreciation equation look when superimposed over the same scatter plot? The graph would be closer to the data points, is what the answer would be. So I'm going to turn my scatter plot, I'm going to turn my plot on. So the easiest way to do it, I guess, is if you go to y equals, arrow up and hit enter. Now plot 1 is on, and I'm going to clear that. Now I want to store that value in there. So in order to store this here, you're going to go to y equals, you're going to press vars, 5 for statistics, arrow over to EQ, and number 1 is regression equation. And it automatically puts that in without rounding. And then if I hit zoom 9 for statistics, there's my scatter plot. And here comes the regression equation of best fit. Okay, that's the exponential depreciation equation graphed with the points given in the table. All right, so example 2 says, what is the depreciation percentage for the 10 years of car prices as modeled by the exponential depreciation equation found in example 1? All right, so I copied the answer over here. I'm going to highlight the part that we need, and that is B. All right, so I'm going to rewrite this. Whoops. What did I press? Okay, pen. I'm going to rewrite this as y equals 25,921.87 times 0.92 to the X. I'm just going to round the B to 2 decimal places. Okay. And we can write this in 2 different ways. We can write y equals A times B to the X, or we can write it as y equals A times 1 minus R to the X. So therefore B equals 1 minus R. Okay, so either way we could have, if you've taken any other algebra classes, you've probably, algebra 2 by the way, you probably would have seen this formula. So now we can set B equal to 1 minus R, and then solving for R, we would get, if I subtract 1 from both sides, then I'm going to get B minus 1 equals negative R. So if I multiply the whole thing by negative 1 and distribute, I'm going to get negative B plus 1 equals R. Okay, or I can rewrite this as R equals and put the 1 first, 1 minus B. And R equals 1 minus B. So since this is our B right here, so I can substitute it in, and I could say R equals 1 minus 0.92, since B is 0.92. So R equals 0.08 or 8%. Okay, and that's per year. The other way I could have done it is just go into my calculator. And since I have it already graphed here, I can hit second table and I can enter a value for R. So if I put a 10 in here, that's going to give me 11,134. And so depreciation percentage for 10 years of car prices, well, that'd be after the 10th year, I guess. I don't think I'd want to do that. But if I put a 1 there, it's 23,821. And 25,921 minus 23,821 would give me a value, and I put that over the denominator of 25,921.87, and I should get 8% that way as well. But it's much easier just to do this if we know that 1 minus r equals b. Okay. All right, so let's check your understanding. It says, after entering a set of automobile value data into a graphing calculator, the following exponential regression equation information is given. Okay, so it gave us our A and our B, just like I did in the calculator on the last problem. And so this is asking us to come to get an equation. All right, so to check your understanding is going to be substitution. So all we're going to do is take y equals, and our A is 32,567.9872 times 0.875 to the x. So it says, after entering the set of data into the graphing calculator, the following exponential equation is given. Round the value of the nearest round the values to the nearest hundredth. Determine the depreciation percentage. So this is the depreciation percentage we did up here. So it says round to the nearest hundredth. So I'm going to say y equals 32,567.99, because that 7 is greater than 5, times 0.88 to the x. So since r equals 1 minus b, we're going to get r equals 1 minus 0.88, or r equals 12%. Okay, example 3. Eamon purchased a 4-year-old car for $16,400. When the car was new, it sold for $23,000. Find the depreciation rate to the nearest tenth of a percent. All right, so we're going to start with the formula. Y equals A times 1 minus R to the X. Okay, so Y is our current value. So now we substitute in. So that's going to be 16,400. A is the initial value of the vehicle when it was new, which is 23,000, times 1 minus R. And the power is the number of years, which is 4. So here's the formula substituted in. We're trying to solve for R. There's multiplication. So first thing we have to do is get rid of this 23,000. So divide both sides by 23,000. These will cancel. And I'm going to divide that now and make it smaller. So it's 16400 divided by 23,000. And I get this number. And let me hit math, enter, see if it's a smaller fraction. I was just going to reduce it to 82 over 115. Okay, and that is going to equal 1 minus R to the 4th power. So to get rid of powers of 4, I could take the 4th root, but that's the same as taking it to the power of a quarter. So if I take both sides to the power of 1/4, and I do that here, answer to the power of 0.25, enter, and hit math, enter, enter. All right, now we're getting into a value that is not calculating properly. So it's 0.91892227. And I'm going to use approximately now. So the quarter to the power of 4 cancels to 1, and we're just going to get 1 minus R. And then to get R by itself, I'm going to subtract 1 from both sides. So in my calculator, I just hit -1, enter, and I get a negative 0.081 equals a negative R. Multiply both sides by -1, and we're going to get 0.81 is approximately equal to R. Okay, so that is going to be 8.1%. Okay, I hesitated there because that didn't make sense. That's 81%, but it's 0.081. I have 0 point, and I forgot my 0 here. 0.081 or 8.1%. Okay, so it's depreciating at a rate of 8.1% annually. Now check your understanding. It says a car originally sells for D dollars after A years. Okay, so I'm just gonna color code these. So let me erase all of this. Okay, and let me highlight using different colors. Here's what the car was worth after a certain number of years, which is our X. And here's the initial value. Right, so now I switch back to my pen. So the initial value is A. The years is your exponent, and the 16,400 is our Y. So now it says, so I have Y equals A times 1 minus R to the X. And it says a car originally sells for D dollars. That's the original price. That goes where A is. So that is going to become D. After A years, the value of the car is dropped. Well, A years is going to be this variable here. So it's going to be 1 minus R to the A. Okay, after A years, the value of the car dropped exponentially to P dollars. So there's the formula. P equals D times 1 minus R to the power of A. All right, so if I want to solve this and get everything all on one side, I'm going to divide both sides by D. And that's going to give me P over D equals 1 minus R to the A. Okay, and then to get rid of that A, I'm going to take it to the power of 1 over A and do the same over here. Okay, and let me move it over to here. So now I have P over D, let me just put it in parentheses, to the 1 over A equals 1 minus R. Okay, and we're trying to get R by itself. So I'm going to subtract 1 from both sides. So this is going to give me P over D to the 1 minus A, or 1 over A minus 1 equals negative R. Multiply everything by -1, and that's going to give me 1 minus P over D to the 1 over A equals R. So it says write an algebraic expression for the exponential depreciation rate represented as a decimal. Okay, so I'm just going to get that out of the way because it didn't say write an equation. It said write an expression for the depreciation rate. So it's 1 minus P over D to the power of 1 over A. And there you have it. All right, example 4. A car originally sold, the original price was $26,600. It depreciates exponentially at a rate of 5.5% per year. When purchasing the car, Richard put $6,000 down and pays $400 per month to pay off the balance. After how many years will the car value equal the amount he paid to date for the vehicle? Okay, so we have two equations. Y equals A times 1 minus R to the X. Okay, that's the depreciation equation. And then there's the equation of the payments, which equals y equals mx plus b. All right, so I'm just going to enter everything that they gave us. So the $26,600 is the original price. That is A. So we're going to write y equals 26,600 times 1 minus r. And actually, we have the r. R is 5.5%, which is 0.055 to the x. Okay, so there's the exponential equation, exponential depreciation equation. And then I'm going to, let's change this color to, I don't know, purple. All right, so then I'm going to continue with this. Well, then we have y equals, well, the slope, the rate of change is $400 per month. So he's paying $400 per month, plus he paid $6,000 down payment. That's our y-intercept. So it says after how many years will his car value, how many years will his car value equal the amount he paid to date for the car? So in order to solve an equation, when the exponent is x, we would have to do the logarithm or natural log. So let's just use a calculator to do this to avoid that process. And we'll just graph both of them. So I'm going to go to y equals and clear this, turn my plot off. And I'm going to put 26,600 parentheses 1 minus 0.055 to the power of x. And then on the other one, I'm going to do 400x plus 6,000. So there's my two equations. I need to adjust my window. X minimum, I want to be 0. X maximum is however many months you're going to pay, and this is years. So I need to make a change right here. I just got thinking about that. Let me go back to y equals. This is a monthly payment right here. This is annual. So I need to multiply 400 times 12. And that is going to be 4,800. So I'm going to adjust this to months. Or years, I mean. So if you pay $400 a month towards your car, that's 4,800 per year, and X is number of years. We have to be in the same format. All right, so now I got to change this. So right here, I'm just going to hit second, insert, and I'm going to insert an 8, 4,800. So now I have the two equations in terms of years. Okay. So now when I go to my window, my X minimum is 0. My X maximum is, yeah, it says 10.9. Let's just leave it at that. Or how about 10 years? The Y minimum, we're not going to go negative. So let's make it 0. And let's make the Y maximum, the cost of the car, 26,600, or let's go a little higher, 26,700, and hit graph. So this is the decay function coming down. It's not linear, it's got a slight curve to it. And there is the linear payment function. We want to know where this crosses. This question was asking, when are they equal? When is the value of the car equal to how much he paid? So if I now hit calculate, I want to calculate second, calculate intersections number 5. Whoops, let me go back to graph. I hit that twice, I think. Second, calculate 5. Now it's asking first curve, okay, the exponential one. Second curve, the linear, and hit guess. It should put the cursor there, and there it is. The car's value and how much he paid is going to be $22,022.74. And it's going to be approximately 3 1/3 years, or 3 years, 4 months. So I would say approximately 3 years, 4 months. Okay. All right, now the check your understanding says, describe the situation pictured above this after 4 years. So what they're saying is, if I were here or here or here, as the years go by, you are paying more and more and more, and the value of the car is going down. So the situation there is the amount he has paid towards the loan of the car is more than what the car is worth. Okay, so there it is in words. The amount he has paid toward the loan of the car is more than what the car is worth. All righty. All right, example 5. A car exponentially depreciates. Okay. Go to highlighter. A car exponentially depreciates at a rate of 6%. IKEA purchased a 5-year-old car for $18,000. What's the original price of the car when it was new? Okay, so let me mark this up. Exponentially depreciates. This is R, which is 6%. 6% is 0.06. 5 years old, that's our X. 18,000 is our Y, and the original price is A. So there's everything all labeled up. So we write Y equals A times 1 minus R to the X. Substitute everything in. Y is 18,000. Okay. Is that clear, hopefully? Simplify. 18,000 equals A times 1 minus 0.06 is 0.94 to the 5th. I want to get A by itself, so I divide by 0.94 to the 5th power on both sides. This is going to give me A equals. So I get my calculator out. And I'm going to put 18,000 divided by, I'll just put parentheses just in case, 0.94 to the 5th. And hit enter. And the original price of the car was $24,526.37. Okay, there's the original price of the car. Now the check your understanding says a car depreciates exponentially. All right, very good. So stop right there. When you see that, you write this: Y equals A times 1 minus R to the X. That's what that tells us. Continuing, 5%, 30,000 after 9 months. What was the original price? Okay, so it's the same type of problem as before. Hopefully you understand it. 5% is 0.05, and that is our R. $30,000 after 9 months, that is our Y. Okay, this is our Y. The original price of the car is A, and 9 months is our X. Okay, so we're going to substitute in 30,000 equals original price of the car is what we're trying to find, times 1 minus 0.05 to the power of X, which in this case is 9. Let me think about that a second. Per year, 9 months. Yeah. So 9/12 of a month, a year is 9 months. This reduces to 3/4 of a year. So 9 months is 3/4. Okay, makes sense. So now let's see what happens. 30,000 equals A times 0.94 to the 3/4. Divide both sides by 0.95 to the 3/4. And let's get our calculator and solve it. So we take 30 grand divided by 0.95 to the power of, and I'm going to put 0.75 for 3/4. And I get $31,176.59. So that's simplified to A equals 31,000. What did I say? Where is it? 176.59. All right, so just be really careful when they say months and years. You need to convert to years. Okay, so there's your check your understanding. Okay, so as I said earlier in this video, we could use the calculator to see where those two lines crossed. Otherwise, we would have to have used a logarithm to solve. Here we can't avoid it. Example 6 says Leah and Josh bought, or is it Leia, like the princess? Princess Leia and Josh bought a used car, Land Cruiser, Land Speeder, valued at $20,000. When this car was new, it sold for $24,000. If the car depreciates exponentially at a rate of 8% per year, how old is the car? All right, so let's see. Used car value, new car value, R. How old is the car? All right, so again, the value of the car now is RY. The original value is A. This is R, which is 0.08. And how old is the car is the number of years exponentially. So if we have Y equals A times 1 minus R to the power of X, and I want to know what X is, I've got to get X by itself. The first thing I do is get rid of this A by dividing both sides by A. So that's going to give me Y over A equals 1 minus R to the X. Okay. So now I'm going to take the log of both sides. You should have learned this in Algebra 2, plus it was also in Chapter 2 in this course. So let me move this down because we're going to need some more room. All right, so I need to get this X out of the way. So I'm going to take the log of both sides. And then we're going to apply the power rule, which means bring the exponent out in front and it becomes a coefficient. So now it's the log of Y over A equals X times the log of 1 minus R. Okay, so we're getting closer. I'm trying to get X by itself. Here's multiplication. So divide by the log of 1 minus R on both sides. These will then cancel, and we get X equals the log of Y over A divided by the log of 1 minus R. Whew. Okay, so there's our equation. We have a Y, we have an A, we have an X, we have an R. Now we just take this equation that solved for X and substitute all of our givens in. You ready? X is what we're trying to find. It's going to equal the log of Y, 20,000, oops, not 2,000, 20,000 divided by A is 24,000. That's all divided by the log of 1 minus R. I'll show it for now. 1 minus R, 0.08. So this is going to simplify to the log of, notice these 3 zeros will go away, This would be 10 over 12, which would reduce to 5 over 6. I just like putting things in the calculator easier. So 20 over 24 is 5 over 6 divided by the log of 0.92. And I put that in my calculator, and we're going to find out how many years that is. So we go the log. Where's my log button? Right here. The log of 5 divide 6 and hit enter. Divided by parentheses log 0.92 and hit enter. And I got approximately 2.187. Okay, so that's going to be approximately 2.187 years, or about 2.2 years. 0.2 years is 2/10 of a year. 2/10 of 365. 1/10 is 3.6 days, so that'd be like 7 days, something like that. All right, something like that, something. So let's just say X is approximately 2.19 years old. All right, so there it is. Now check your understanding. Do you understand? Let's slide this up here so we can see our new formula. Solve for X. Now it says, how old would the car in example 4B had it been purchased at half its value? Okay, so what they're saying is, what's going to change here? The Y. Right here. This 20,000. The original value is 24. So in this example here, it'd be like doing this problem here where this is 12,000. Okay, and where was the 20? It was right here. So our answer to this is going to be X equals the log of half price divided by original price divided by the log of the same rate of 1 minus 0.08, which is 0.92. Okay, so that's how we're going to answer this question. So X is going to equal, well, 12,000 over 24,000 is a half, so that's a log of a half divided by a log of 0.92. And since I'm doing fractions or decimals in the denominator, how about I do a decimal in the numerator? 0.5. That's a half, right? So I go to my calculator, clear, log 0.5, enter, divide, log, oops, let me use parentheses just in case. I like to use parentheses and make sure I'm doing it right. 0.92, close the parentheses for the log and the denominator and hit enter. And X is 8.313. So X is approximately 8.31 years. So at about 8.3 years, that vehicle will be worth half of what it was new. Okay. Okay, example 7, according to an online company that supplies used car history reports, a certain make and model car has the following values based on its age. The original price of the car was $24,000. So there's the original price. Then there's 1 year, 2 years, 3 years, 4 years, 5 years. If the pattern continues, what would the car be worth when it is 6 years old? If the pattern continues. All right. So the first thing we're going to do is see if it's an arithmetic sequence. If you don't remember that, that is when you have a common difference, D. So what you do is say, okay, 24,000 minus 21,600 is, oops, undo. 0 minus 0, 0 minus 0. Now I need to borrow 10 minus 6, 3 minus 1. A common difference of 2,400, not common difference, a difference of 2,400 between the first and second term. Now I'm going to check the difference between these two terms, 21,600 minus 19,440. And obviously it's not the same, I can tell already. 2,160 is not equal to 2,400, so there is no D, common difference. This is not arithmetic. Okay, so since these do not have a common difference, we want to see if they have a common ratio, which would be a geometric sequence. Okay, so, or a geometric progression. So we're looking for a common ratio, R. Ratio means fraction or a comparison of two numbers. So let's check. So what we're going to do is take the second term over the first and the third over the second and so on. So for example, if we had 3, 6, 9, 12, 24, 3 times 2 is 6. Whoops, no 9. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So we have an R that equals 2 for this quick example. And if I take the second term divided by the first term, I get 2. If I take the third term divided by the second term, I get 2. If I take the fourth term divided by the third term, I get 2. And so on, and so on, and so on. So R equals 2 because they're all the same. That's just a quick example with more basic numbers. So now we're going to try to do it with these. 21,600 divided by 24,000. So I put that in my calculator. I get 0.9. If I take 19,400 and divide it by 21,600, okay. So now I'm going to do 19,400 divide 21,600, enter. Okay, I get approximately 0.9. If I take 17,496 divided by 19,440, okay, 17,496 divide 19,440, I get 0.9. Oh, I see what I did wrong here. 19,400, it's 19,440. Let me fix that. 19,440 divided by 21,600 is 0.9. Okay, so it isn't an approximation, it's exact. And the last two, I'm assuming, would be the same. So I'm not going to go any further. The common ratio R equals 0.9. All right, so we found R, common ratio. Once that's done, what we're going to do is, in algebraic terms, now we have to come up with the geometric sequence. So if you have a second term, a sub 2, we call it, that's going to equal the first term times R. Okay? The third term is going to equal the second term times that same R. And a sub 4, the fourth term, is going to equal the third term times R. Okay, but since a sub 2 is a sub 1 times R, then we would then get a sub 3 equals a sub 1 times R times another R, which would equal a sub 1 times R squared. And in this situation, we're going to get a sub 4 equals a sub 3, which is a sub 1 times R squared. There's my a sub 3, right? A sub 3 equals this. Substitute that in times this R here. And that's therefore going to equal a sub 1 times r to the 2 times 2 plus 1, which is 3. So the pattern emerges, and so therefore we take a with n number of terms, and that is going to equal a sub 1 times our common ratio to the power of n minus 1. So see how this was a sub 4? It's the first term times r to the third. A sub 3 was the first term times r squared, one less. So a sub n is going to equal a sub 1 times r to the nth term minus 1. So this is the geometric sequence equation, and we know r is 0.9. So if the pattern continues, now we're going to substitute this in. We're going to say a sub n equals a sub 1 times 0.9 to the n minus 1. All right, so let me just get all this out of the way now that we've formulated it. And I know my r is 0.9, so let's just simplify it to a sub n equals a sub 1 times r to the n minus 1. So we're now finally coming together and answering this question. So what does the question ask? What would the car be worth when it is 6 years old? Okay. So this is the original price. 1 year old, 2 years old, 3 years old, 4 years old, 5 years old. What would the car be when it's 6 years old? Okay. So we are going to take we're going to call this a sub 6 equals a sub 1, which is 24,000, times 0.9 to the 6 minus 1. So a sub 6 is going to equal 24,000 times 0.9 to the 5th power. So if I do that, I'm going to get 24,000 parentheses 0.9 to the power of 5. And the answer is 14,171.76. Okay, and so the value, so there it is right here. That's a sub 6, a sub 1, 2, 3, 4, 5, 6. Okay, all right, so since we found this here and that matched, now we're going to do a sub 7. That'd be the next term. A sub 7, a sub 1 being new, a sub 2 being the first year. So a sub 7 is the 6th year. All right. So a sub 7 is going to equal 24,000 times 0.9 to the 7 minus 1, or a sub 7 equals 24,000 times 0.9 to the 6. So if I go here, all I got to do is hit second enter, change this 5 to a 6 and hit enter, and it's 12,754.58. Okay, so the value of the vehicle after 6 years is $12,754.58. Okay, so now we can find the depreciation rate because we're going to need it for your check your understanding. So let's find the depreciation rate. So since our 0.9 is our B, okay, so let me highlight that. This is where this is coming from. 0.9 is our B. Remember, it's y equals a times b to the x. 0.9 is our B. So if I know that B equals 1 minus R, and B is 0.9 equals 1 minus R, and I subtract 1 from both sides, then I get negative 0.1 equals negative R, therefore R equals 0.1 or 10%. Okay, so that is the depreciation rate, 10%. That's how you find that. All right, so now let's take a look at, check your understanding. And it says the original price of the car is $20,000. The car's yearly depreciation is shown by the first four terms of the sequence of being A sub 1, A sub 2, A sub B 3, A sub 4. What is the depreciation rate of the car? And what will the car be worth after 5 years? All right, so the original price of the car, that is, now if you don't remember, we can go back. Okay, when the car was new, that's A. Okay, the original price of the car is A. X is the number of years, and this is A sub 1, A sub 2, A sub 3, A sub 4. So it says it is a geometric sequence we don't need to check, but we want to find what the common ratio is. So I'm first going to start with the second term divided by the first term to get my R. So 17,200 divided by 20,000 is 0.86. Okay, so my R is 0.86. Up here, R was, going back to the last problem, 0.9. That's our B. So now I'm going to write A sub n equals A sub 1 times 0.86 to the power of n minus 1. Okay, and since 0.86 equals 1 minus r, and I subtract 1 from both sides, I'm going to get a negative 0.14 equals negative r. So r equals 0.14. Okay, so there's our r, 0.14. Okay, so that is a 14% depreciation rate. All right, so that's that piece. So let me erase all of this now. And now it says, what will the car be worth when it is 5 years old? So we're going to take, now that'd be A sub 6, right? Because new is year 0. First year is A sub 2. So 5 years would be A sub 6. So I want to find A sub 6, which equals A sub 1 times R to the n minus 1. Okay, and A sub 1 is $20,000. So A sub 6 is going to equal $20,000 times 0.86 to the 5th power. So my 6th term is going to be 20,000 parentheses 0.86 to the power of 5. And my answer is 9408.54. Okay, so the car after 5 years would be $9,408.54. All right, that is the end of chapter 4.6. I hope this all was understandable. Hope you understood it, I guess. Have a great day. Thanks for watching and peace. Ciao, ciao.